All right, let's dive in. You know those calculus problems, right? The ones with the sliding ladder or the growing shadow that just make your head spin? Well, if you've ever felt completely lost staring at one of those, you've come to the right place. Today, we're going to demystify one of the trickiest topics in calculus, related rates. And I promise, by the end of this, you'll have a clear, powerful blueprint to conquer them.
So to get our heads in the game, let's just think about something real. Imagine you're driving up a steep mountain. You've got your speed, right? The road has a certain steepness, and your altitude is obviously changing. You already know these three things are connected. I mean, it's intuitive. If you drive faster or if the road gets steeper, your altitude is going to change a lot more quickly. Well, that connection, related rates, is a language calculus gives us to describe it perfectly. So let's start by building that core intuition. Welcome to Section 1, Calculus of a Changing World.
You know, this quote from a Reddit user just nails it. It says, you can multiply the slope of the road, that's dE over dx, how steep it is, by your velocity, that's dx over dt, how fast you're moving, to get dE over dt, which is how fast your elevation is changing. It's a direct relationship. We're connecting the rate of change of one thing, your speed, to the rate of change of another, your altitude. And it's all linked by a fixed property, the steepness of the road. That right there is the heart and soul of related rates.
So that brings us to the official definition. A related rates problem is basically any time we're trying to find how fast something is changing, but we do it by linking it to other things that we already know the rates for. It's all about being a detective and finding that hidden connection between all the moving parts. Okay, so how do we actually do this with math? Well, that brings us to Section 2, and this is the big one, folks. You've got to respect the time derivative. This idea is the absolute key to the kingdom. Here's the most crucial idea you need to grasp. In the world of related rates, time is the invisible thread connecting everything. The ladder's position, the shadow's length, a balloon's volume, they're all changing as time, little t, ticks forward. So what does that mean? It means every single derivative we take is going to be with respect to time. And this slide just lays out the difference perfectly. Look on the left. If you differentiate x squared with respect to x, you get 2x. Easy, we've done that a million times. But now look at the right. When we differentiate that same x squared with respect to time, we have to use the chain rule. We still get 2x, but then we have to multiply by the derivative of the inside stuff, which is x with respect to t. That gives us that extra term, dx dt. And that little piece right there, that's the whole ballgame. That's the rate in related rates. All right, so we've got the core concept down, but how do we apply it without getting lost? Welcome to Section 3, your 4-step blueprint. This is the game plan, the strategy that turns a confusing word problem into a totally manageable process. Just follow these 4 steps and you'll be golden. Step 1, identify and relate. And I'm serious about this one. Draw a picture. Label everything you know and what you need to find. Then dig up an equation from geometry, like the Pythagorean theorem or similar triangles that connects your variables. Step 2, differentiate. Take that entire equation and hit it with a derivative with respect to time. Step 3, now, and only now, can you plug in all the numbers you know. And finally, step 4, just do the algebra and solve for the rate you were looking for. Okay, I've got to call a timeout here for the single biggest mistake people make. Do not substitute numbers for your variables before you differentiate. If you plug in, say, the ladder's distance from the wall before you take the derivative, you're telling calculus that distance is a constant. Its derivative becomes 0, and your entire calculation just falls apart. You have to differentiate the general relationship first, and then plug in the numbers for that specific snapshot in time. Okay, enough theory. Let's get our hands dirty and actually see this blueprint in action. Time for Section 4, ladders, shadows, and solutions. So here's the classic problem. We've got a 20-foot lamppost and a 6-foot-tall man walking away from it. We know his speed is a constant 5 feet per second. The question is, how fast is the very tip of his shadow moving along the ground? Step 1, identify and relate. The picture here is key. You can see 2 right triangles, right? There's the big one made by the lamppost and the full shadow, and a smaller one made by the man and his part of the shadow. They're what we call similar triangles. Same shape, different sizes. That means the ratio of their heights, 6 over 20, has to equal the ratio of their bases, y over the total distance, x plus y. And there it is. That's our geometric link. That's the equation that connects everything. Step 2, differentiate. Now we could work with that fraction, but let's make our lives easier. A little cross multiplication and algebra simplifies that equation to 14y equals 6x. Much cleaner.
Now we hit both sides with the derivative with respect to time. The derivative of 14y becomes 14 times dy dt. The derivative of 6x becomes 6 times dx dt. And look at that. We now have an equation that relates the rates, the speeds. Now for the home stretch, steps 3 and 4. We know the man's speed, dx by dt, is 5. But hold on, there's a little twist. The question asks for the speed of the tip of the shadow. If you look at the diagram, the tip's total distance from the lamppost is x plus y. So the rate we actually need to find is the derivative of that whole thing, dx by dt plus dy by dt.
So first we use our differentiated equation from step 2 to solve for dy over dt, which is the speed the shadow itself is getting longer. Then we take that number and add it to the man's speed, dx over dt. The final answer? The tip of the shadow is moving at a constant rate of 50 over 7 feet per second. That's about 7.14 feet per second. See? The blueprint works perfectly.
So this is awesome for passing a calc test, but who cares, right? Why does this actually matter in the real world? Well, let's find out in our final section. From ladders to pandemics.
It turns out that the simple logic we just used, find an equation, then differentiate it with respect to time, is the fundamental building block for something way more powerful, ordinary differential equations, or ODEs. These are the tools that scientists and engineers use to model pretty much any complex moving system you can think of.
And don't just take my word for it. This quote comes from a research paper about a tool used to model diseases. It shows that this exact mathematical thinking is used to fight global crises like Ebola, MERS, and the H1N1 pandemic. Epidemiologists create equations that relate the rates of how many people are susceptible, infected, and recovered. It's the same core idea we used for the man and his shadow.
So, from the speed of a shadow on the pavement to the spread of a global virus, the logic of related rates gives us this incredible lens to understand our changing world. Which really leaves us with a final question to chew on. What other complex, dynamic systems out there, from stock markets to climate change, could we understand better just by figuring out how all their rates of change are related?